Okay, everyone sees and hears me appropriately, I guess. Let's see. And we can draw. Ooh, it's blue right now. Okay, so apparently this winter will never end, and we get snowstorms every single day now. This one, I don't know, I feel like the university could have stayed open, but that's just my opinion. So hopefully everyone is staying cozy and warm. Uh, so what we're going to talk about today is to go over more of the reaction energy balances, but I wanted to start off with sort of just a confidence boosting sort of overview. So I know it seems very confusing that we have this method for heat of vaporization, this method for that, and there's a bunch of other methods going around. But I want to sort of step back and try and tie it all together. So on Friday, I think we talked about if we were to plot the enthalpy versus temperature for a vapor and for a liquid, right? And this is an oversimplification. These lines are not necessarily straight, right? At the critical point, right, we will have the vapor and liquid be the same. So this is V, this is L, right? So the heat capacity is going to be the slope, rise over run, right? So heat capacity is defined as the rate of change of enthalpy with respect to temperature while holding the pressure constant. So in this drawing here, this is not 100% accurate because the pressure is changing a bit too, but as a point of discussion, I think it's totally valid. At the normal boiling point, call that Tn for any given fluid, right? This is where we will typically measure what the heat of vaporization is. So delta H of vaporization is going to be the enthalpy of the vapor minus the enthalpy of the liquid, right? The vapor has a higher enthalpy, liquid has a lower enthalpy, so this number is going to be greater than 0. Now, if we were to define the heat of vaporization opposite, where it was liquid minus vapor, then it would be negative. But this is just the convention that we sort of define this term as. We talked about a rock climbing analogy where if you were down here and you wanted to get up there, you could choose a path that went all the way around to here. And that's totally valid. So what you would need to have in this circumstance is heat capacity as a function of temperature and pressure, and then you could just integrate it along whatever path that you choose, right? It would make more sense to maybe go straight out to some temperature, straight up, straight over, straight down, right? We could also go through the point where we have the data. And that's exactly the procedure that we showed when we were talking about energy balances on a flash separator, right? We heated up the liquid to the normal boiling point, we boiled it, and then we cooled down the vapor to the conditions that we actually had. Now, we also have correlations that we can use. But ultimately, in thermodynamics, we have a couple of key measurements that we need to make, and we can actually unlock all of the fluid properties. So thermodynamics is a very nice field of study where it seems really complicated, but it actually reduces most all materials into a couple of properties that we measure. And so when I teach thermodynamics at the graduate level, what I always try and communicate is that I'm teaching the system of thermodynamics, right? There's only a handful of equations that we have to have in thermodynamics, and then everything else is just a convention that we've created. So for example, we already have heat capacity here, right? This is defined. We can also define heat capacity as 1 over, actually, no, let me not do this one here. Let me just write out this way. So we can write delta H is equal to the integral of C sub P dt. We can also show that the change in entropy is the integral of C sub P over T dt. If we combine these together, we can get something called the Gibbs free energy. And the Gibbs free energy of a liquid is equal to the Gibbs free energy of a vapor, and that's how we know where phase changes occur. So with one simple property measurement, the heat capacity, We can then basically estimate how much energy does it take to heat something or cool something, how much the entropy changes when you heat or cool something. By combining the two together, we can figure out where phase changes occur, right? So the one thing that I wanted to go over on this is that when we talk about the reacting systems, we talked about the heat of reaction method and the heat of formation method, and we've got another method for estimating heats of vaporization at different temperatures away from the normal boiling point, but the same concept applies. We're basically just unpacking these definitions that were provided. So let's go to the reacting systems. So we talked about two approaches. One was the heat of reaction method. And in this method, we have an energy balance that is written as the summation over all of the terribly drawn extensive reaction plus the enthalpy leaving minus the enthalpy entering, right? And so we get the plus out and minus in. That's just because we move everything to the other side of the equation. So if we start off with the general energy balance, du dt, in a steady state process, this is equal to 0. Here we are summing up enthalpy in, we're minusing all of the enthalpy out, plus Q plus W minus P dV dt, which then is going to go to 0 for most of our open steady processes. If we don't have any work, this goes to 0. So then if we're solving for how much heat is being evolved or how much heat we need to put into the reaction, right, we move these two terms to the other side, and that's why our signs are flipped. That's why we have the out minus in. But if we're just keeping track of our accounting, it's in minus out, but then we have this Q and the 0 over here. So the second approach is the heat of formation method. What I want to clarify is that these are mathematically exactly the same. And the only difference is where do we include some of these enthalpy terms. So in the heat of formation method, Q, we're just going to keep track of out minus in. And today I'm going to go over an example or a couple of examples. Okay. So the only difference is that for a chemical reaction, the delta H of reaction, and the little knot here, remember this means at the standard state, so 25 degrees C and 1 atmosphere pressure. This is the stoichiometric coefficients multiplied by the heats of formation for each of the individual species.
So I just have a quick question.
Yes.
So sometimes you write H of R naught and sometimes you write H of reaction naught. Are they the same thing?
Yeah, they're the same thing. I guess
Okay.
sometimes I'm just trying to be quick and write
Yeah.
R. Sometimes I'll write reaction.
Okay, just making sure.
Yeah, but this is the same as this. So the only difference, and this pertains to homework 4, number 4 of the homework. The only difference between these two approaches is where do I put this information? In the heat of formation method, I include this heat of formation inside each of these individual enthalpies. In the heat of reaction method, I include this heat of formation information into the delta H of the reaction. But the concept is the same. We're just choosing a path through which we know the data. So I don't want to go in the lab and measure the heat of vaporization for every fluid at every different temperature. But I don't have to. If I measure the heat capacity of the liquid, I measure the heat capacity of the vapor, and then I measure the heat of vaporization at one state, that just greatly simplified the number of experiments I have to do, right? So I really need to make 3 measurements: heat capacity of liquid, heat capacity of vapor, and then just the heat of vaporization at one point. Now, if I want to do reactions, I only need to add one more experiment, and that's the heat of formation. How do I get the heat of formation? Well, the easiest way is to just burn all of the reactants and all of the products to make CO2 and water, like if it's a hydrocarbon reaction. Then using Hess's law, I can figure out how much energy it would have taken to create those for the heat of formation. So that's what basically we're doing. We synthesize a material, we purify it, and then we burn it. And we measure how much energy comes out when we burn. And if we do that for all of the different chemicals in the system, we can figure out what the heat of reaction is and the heat of formation is. So now I can do any chemical reaction with any material, and I basically need just 4 measurements. How much energy does it take to heat the liquid? How much energy does it take to heat the vapor? How much energy does it take to vaporize it? And how much energy does it take or release to create the molecule? All these other strategies we're talking about are just different paths that you can choose. But based on what data you have, you can choose your own path. Okay, so let me just go over a little bit of what the homework would be. So I believe we have one that's, I think number A is delta H of formation for ethylene glycol. Ethylene glycol. Does anyone know what ethylene glycol is? And I've guaranteed every single one of you has used it at some point in your life, or you've been around it, maybe not to your knowledge. Anyone know what ethylene glycol is used for most consumers?
Coolant.
Coolant, so it's antifreeze. So it is the antifreeze that is generally mixed with water. The reason why they mix it with water is actually it'll have a higher boiling point when it's mixed with water, I believe. So it's that's what they do to blend. Okay. So in this one, what I'm asking in the homework is for you to come up with the enthalpy that you would put into a table in order to balance this heat of formation method. So if I were to build a table, right? So it's chemical A, chemical B, chemical C, chemical D, right? I'm going to have an N in, an enthalpy in, a molar flow rate out, and an enthalpy out, right? So in the first exam, we talked about balancing reacting systems. So we're going to have numbers for the flow rate in and out of all of these different chemical species. Then in order to do the energy balance component, we need to find enthalpy values for each of the reactants and products in and out. Now, most all chemical reactions on an industrial scale are going to be partial reactions, and that's why we have the reactor separator, so we can recycle back all of the unreacted material. But the number that you want to put into this table so that you can very easily calculate the summation of the flow rates and enthalpies, right? That would be the sum of NiHi in. This down here would be the sum of NiHi out. And then once we have this table set up, the energy balance becomes really straightforward. It's just a plug and chug, big algebraic expression, right? So that's what I'm asking for in number 4 of the homework. So for ethylene glycol, I believe it's at 400 degrees C and 1 atmosphere pressure. So because ethylene glycol is antifreeze that we put in our cars, that means we know it's basically a liquid when we synthesize it, okay? So the enthalpy of ethylene glycol at 400 degrees C and 1 atmosphere, right? This is the value we would put into that table. And we would have to do this for the other chemical reactions and reactants and products as well, but this is just for that one material. In the heat of formation, we would do delta H formation naught of ethylene glycol, right? This is something that someone else has measured, we can look it up in the back of the book. Okay, so boom, we've created ethylene glycol from carbon, hydrogen, and oxygen. Okay, we've created the molecule, and this is going to have some delta H, probably some relatively large number, because ethylene glycol is a fairly big molecule. Then we have to go from ethylene glycol at the standard state, and we would have to look up what state of matter it's going to be in. Is ethylene glycol a gas? Is ethylene glycol a liquid? Once we figure out what phase it's in, that means we look up the normal boiling point, or we look up its vapor pressure curve, so that at the temperature and pressure that we're working at, we know what phase it's in. So we know that ethylene glycol, if we look it up and check the vapor pressure or the boiling point, that this is a liquid. So then we need to heat up from the reference state of 25 degrees C all the way up to the normal boiling point, which I don't have off the top of my head. But again, this is something that can be readily looked up in the back of the book. We are going to heat it up using the heat capacity of the liquid until we get to the normal boiling point. Then we're going to vaporize it, right? The delta H of vaporization at the normal boiling point, right? So we're going from atoms, carbon, hydrogen, and oxygen to ethylene glycol. That's step one. Then we heat the liquid ethylene glycol to its normal boiling point. That's step two. We go from a saturated liquid to a saturated vapor. That's the third step here. And then the final step is we go from the normal boiling point of a saturated vapor to the 400 degrees C final state. But instead, now we're heating up the heat capacity of the vapor. And so this would be part A of homework problem number 4, is you would have to look up different data resources to estimate what this is going to be. Now, in that problem, I say you can make assumptions. So what if you found only constant heat capacity for the liquid? Well, then we could assume that the heat capacity is constant and that this term here would then be C sub P dB minus 25, right? For example, if you had a constant heat capacity for this one, then it would C sub P, liquid and vapor, 400 minus the normal boiling point. Okay. Now, for the other problems, some of them say now you use the heat of reaction method. Well, in the heat of reaction method, we just get rid of this term here. So in the reaction method, the reference is the molecule at 25 degrees C and 1 atmosphere. In the formation method, it's the atomic species. Okay. Questions on this? Seems okay then. So if I'm using the heat of reaction method, I start off with the molecule at 25 degrees C and 1 atmosphere. If I start off with the heat of formation method, I have individual Lego building blocks of atoms, and I first have to create the molecule. So then if we go back to our two energy balances, the only difference is where do I put this delta H of formation information? I either put it directly in the enthalpy term or I lump it together in this delta H of reaction. So my general guidance is going to be do this for simple systems. Let's say you have a reaction that goes 100% to completion in stoichiometric ratios, only one chemical reaction occurring. That's when you want to use the heat of reaction method because you'll be a little bit more efficient. Heat of formation method, this is going to be for complex systems. So let's say you have multiple chemical reactions that are all going to some partial reaction completion. Instead, with the heat of formation method is you don't actually have to worry too much about how much extent 1 is, how much extent 2 is. Once you solve the material balance using atom balances, molecular balances, or extensive reactions, you don't actually care. You don't actually care what reactions are occurring. You just need to know this number of moles are coming in, this number of moles are coming out. And then you can basically just calculate all the enthalpies and it'll all work out. Yes, Ethan, question.
So using the heat of formation approach, will we then be doing our like correction factors from the standard operating, the STP that the heat of formation was calculated at on like the individual, like for say CO2, we'd be doing it on carbon and oxygen, or will we still be doing those corrections on the whole molecule of CO2?
You would do it on the whole molecule of CO2. So for example, if we were to go back to your question, so let's say we had some chemical reaction, let's say with CH4 plus 2O2 goes to CO2 plus H2O, right? So let's just think of some reaction that involves carbon dioxide. So if I wanted to know what is the enthalpy of my carbon dioxide, okay, and I'm using the heat of formation method. So what I would need to do then is the enthalpy of CO2 would be equal to first creating the CO2, right? And this would be from carbon plus O2, right? Boom, I react carbon and O2 and I make CO2. Then at 25 degrees C in 1 atmosphere, CO2 is going to be a gas, so then it's relatively straightforward. Then I would just integrate from my reference state to whatever the system temperature outlet is here, the heat capacity of vapor CO2 dt. And this is the enthalpy that I would put into the table.
Okay, that makes sense. So if we were
Yep.
actually balancing a whole system, then we would have to do it for carbon and oxygen for their enthalpies, but like to get them from whatever the inlet temperatures are to the STP.
So if you were measuring this delta H of reaction for the very first time, you would have to do all of those calculations. But because the heat of formation for water has already been measured, for methane has already been measured, you can just directly do exactly the same procedure for all of them.
Okay, that makes sense.
Yeah, so if you wanted to figure out what the delta H of reaction was, you could take methane. Well, in this case, this is pretty easy because this is just the combustion reaction, right? You would burn it, okay, and that would give you the delta H of reaction. So if I burned burned methane and oxygen, and I got CO2 and water, I could measure this delta H of reaction, right? Then I could figure out what is the delta H of formation for water, what is the delta H of formation of CO2. The delta H of formation for oxygen is 0. And so from that, I could infer what the formation energy was for the methane. So the very first time that someone had to do this, they had to go through all that process. But now you can just look it up. So this formula right here, if this is all gas phase, will be exactly the same for all 4 of the reactants and products. The only thing that would change, instead of CO2, I would put CH4, CH4, CH4. For water, 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 water. The only difference is here, I'd have to make sure I use the heat of formation for H2O vapor, which is also tabulated as well. And so the nice thing about this whole process is that it's very algorithmic. So then we can just build a table, and let me just show you how I would set this up, okay? So what I would say in that example, I would build a table, CH4, O2, CO2, and H2O. So then I would say, I would go to the back of the book and I would look up delta H formation, heat capacity of liquid, heat capacity of vapor, and I can maybe even put in TB for the normal boiling point, right? So I could look up all my physical properties. And I could say, okay, methane heat of formation, got that number. Oxygen's heat of formation, that's just 0. CO2's heat of formation, that's a number. Water's heat of formation, that's a number. And then I can fill in all the heat capacities, all the normal boiling points, right? And then I can basically build my table where I have CH4, O2, CO2, H2O, and in, enthalpy in and out, enthalpy out, right? And then for methane, I would build my formula, delta H formation plus integration from 25 to T, C sub P vapor dt, right? And then I would reference these cells. Then if I drag this equation down, I would be populating all of my calculations and I only have to type in one formula. Does that kind of make sense how that works, everyone?
Yeah, that's crystal clear.
Yeah, good.
Thank
So
you.
then, that's why it's sort of nice. So then the only difference between methane and water from a thermodynamic perspective is its heat of formation different? Is its heat capacity different? What's its boiling point? Right. So those are the only differences from a thermodynamic perspective of these different fluids to determine how much energy goes in and out of the process. So these methods, right, the system of thermodynamics uses confusing and archaic language, but the end result is a really algorithmic, sort of straightforward calculation. Once you understand that, you just have to choose pathways to calculate delta H's that go through data points where you have those physical property measurements. So depending on what access to data you have, you may have to choose slightly different pathways for different systems. So in this case here, the heat of formation of water, CO2, oxygen, and methane, all of those are available in the vapor state. So you can, boom, create all the molecules as a vapor and then just heat them up as a vapor. But if you have some materials that are liquid at the standard state, then you'd have to go through the additional step of calculating its enthalpies as the vapor. Or if you had a reaction that was colder than 25 degrees C, you would create the molecule at 25 degrees C, and you'd have to cool it down to whatever the system condition is. Okay, so let's go through a couple of examples before we run out of time and I get too long-winded. I have one here for ammonia synthesis. So we have N2 plus 3 hydrogens going to 2 ammonias. Okay, now this is almost the formation reaction, right? The formation reaction is going to be 1/2 nitrogen plus 3/2 hydrogen going to 1 NH3, right? We're forming one ammonia molecule. This would have a delta H of formation of 46.19 kilojoules per mole. Now, most molecules will have a negative heat of formation, at least a lot of the ones that we deal with. But some materials will have a positive heat of formation. So what that means is that these bonds between the nitrogen and hydrogen, they're actually a lower energy state than actually being bonded together. Now, this has a couple of good utilizations for ammonia. So ammonia is a relatively high energy material, so it's fairly reactive. And that means that we can take this ammonia and react it with other materials so that we can get that nitrogen into soil. So this is the Haber process, or the reaction that underpins the Haber process, which is what a very large fraction of the nitrogen in your body right now comes from. So it's good that it's somewhat of a higher energy. And also ammonia is being investigated as an alternative fuel. So if you can create ammonia, you can liquefy it fairly readily. The higher the energy the NH bonds have, the more energy you can get out if you were to burn it. And if you were to burn ammonia, you would get, hydrogen that would then react to form water, and then you just get nitrogen. So it'd be a fairly clean burning fuel, but ammonia itself is fairly hazardous. So as written, right, I chose to write my reaction this way. So then the delta H of reaction would be equal to 2 times the delta H of formation for this particular one, right? Because it's half nitrogen, it's 1 nitrogen here. So the delta H of reaction, as I've written it, then is going to be 92.4 kilojoules per mole. Now in my reactor, we're going to feed in stoichiometric ratios. So 1 mole of nitrogen, 3 moles of hydrogen. It's going to react. We have some heat input that is required to complete this process, and we're going to make 2 moles of ammonia. This process is going to occur at 1000 degrees Celsius and 30 atmospheres. Okay, so our goal is solve for the Q to do this process. So this is an example where it's relatively straightforward. It's a complete reaction, so maybe the heat of reaction method will work. So what we're going to do, and let me write out the energy balance here for the heat of reaction method. So we have extensive reaction, delta H of reaction plus okay, so that's going to be our energy balance. If we use the heat of reaction method, that means our reference state is going to be the individual atoms themselves. Okay, so I got to keep checking the chat. Oh, so someone is saying it makes a ton of NOx as well. Yeah, that's I think the big challenge right now is completing the combustion of the ammonia. I'm not convinced it's going to be a successful technology, but hey, people are trying out ideas. Okay, so the way to think of the heat of reaction method is, let me go back to the very beginning when we talked about this heat of vaporization cliff example, right? So if I want to know the heat of vaporization where we don't know what the heat of vaporization is, we go through a path where we do know the heat of vaporization. We're going to do the same thing, but going through a path where we know the heat of reaction. And where do we know the heat of reaction? That's at 25 degrees C and 1 atmosphere pressure. So we're going to have to manipulate our reactants, go to 25 degrees C, react it, and then get it back up to the process conditions. So let's do that. So step 1 is we're going to cool the inlet to 25 degrees C and 1 atmosphere. So we're going to cool and depressurize. Step 2, we are going to react at 25 degrees C and 1 atmosphere. And step 3, we are going to heat outlet to, what do we have? 1000 degrees C and 30 atmospheres. So we're going to heat and pressurize and then cool and depressurize. So the first thing I just want to make clear is that the signs of these approaches are going to be flipped, but it's all taken into account by this negative sign here. So in the heat of reaction method, we're going to create our molecule, right? The molecule is already going to be created, and we're just going to heat to the actual conditions. So in the case of the nitrogen, we're going to start off with just pure nitrogen itself. And then the enthalpy value that you would put into your table would be heating it up to 1000, pressurizing it to 30 atmospheres, right? But then it's going to be minused out. So that's the same thing as if we were to cool it to 1000, right? That's a negative enthalpy. Ethan, question.
Oh yeah, I was just gonna say. So, if we're told that a system operates at like 1000 degrees C and 30 atmospheres, is it safe to assume that that is the inlet conditions of like the incoming reactants?
In this particular example, it's an isothermal process. So the inlet and the outlet are going to be the same temperature. But in a different type of problem, we would say this is the inlet temperature, this is the outlet temperature, how much heat. Or
okay, so it'd be specified then.
Yes, yeah. So in this particular example, it's just constant temperature, just to get us to get through the problem.
Okay, gotcha.
Okay, so step 1, right? We're going to cool everything down to the inlet condition. So we have a PT little diagram here just to highlight what we're doing, right? So this is the inlet conditions, and this is the standard state down here, right? So this is 25 degrees C. This is 1 atm. This up here is our 30 atmospheres, and this is our 1000 degrees C, right? So we're going to calculate the delta H, and this is the same for the hydrogen or the nitrogen, right? So it's the same path, just different properties, different heat capacities, right? So the first step is we're going to do, I'll call this delta H1, delta H2. So we're going to go from this one here, going from 30 to 1 atmosphere. This is a gas phase, so the enthalpy of an ideal gas is independent of pressure. So this first step, depressurizing from 30 to 1 atmospheres, this is going to be assumed to be 0 for the sake of our calculations. So ideal gases, the pressure does not affect the enthalpy. For liquids, it does, but it's a small effect. So it's something you only have to worry about a little. So for enthalpy 2, this is, we're going to integrate from 1000 to 25, the heat capacity of the vapor dT, right? So we've gone from our inlet conditions down to our state. Now you'll notice that these two signs are flipped, right? So 25 and 1000, when we do the reference state, we go from 25 to 1000. This one we're going from 1000 to 25. So in the example that I'm showing here, I'm walking us through the pathway, but it's all accounted for in this format here where you have out minus in. So that's where this minus sign, that corrects for that. Step 2 is we are going to react the system. So delta H, the extent of reaction, times by the delta H of reaction is equal to 2 times the delta H of formation. And in this particular example, based on the material balance, the complete combustion, the extent of reaction here is equal to 1. So I have one chunk of this going to that, and it's a complete reaction. The final step is we're going the opposite. So P and T. This is for the ammonia. So we're going from 1 atmosphere to 30 atmospheres. And you guys can probably all hear my dog barking right now.
I have a quick question. So in step 2, you did delta H of formation, and then there's like a little something.
This
yeah.
squiggle, this here, forget about it. This little knot here. This is for at 25 degrees C.
You just don't have any ratio. Okay, just make sure.
Yeah. Let me just shut my door really quickly. All right. So then now we're going to heat our product, in this case it's ammonia, to go from the reaction conditions to the outlet condition. So then there, the delta H is going to be integral from 25 to 1000 C sub P of the vapor dt plus delta H2. So in this case, this is step 1, this is step 2. The energy for the pressurization, we're going to say, is equal to 0 as well. So if we put it all together, okay, the delta H, which is going to be equal to the heat, is going to be the flow rate of the nitrogen plus the delta H from 30 to 1 atmosphere plus the delta H from 1000 to 25 plus same thing for hydrogen plus the extent times the delta H of the reaction at the standard state. And then finally, the product, delta H going from 1 to 30 atmospheres plus heating from 25 to 1000 degrees C. And so when I was talking about the signs, just because I think I wanted to walk us through the process of like cooling it, reacting it, and heating it. but it does introduce a little bit of this sign confusion, right? So you'll notice this is plus, 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 plus. If we go back to our energy balance, right, we have plus the out and minus the in. And that'll work out just fine, because if we swap the 25 to 1,000, that makes it a negative integral. So it's the same, it's consistent, but the signs kind of take that into account. So I don't know, Thomas, do you have a question, or you just
I realized
flash
the
raise
answer to it.
Oh, okay. I have a question here from Andrew. For part one, did you say for gases, delta H doesn't change when you change the pressure? Yeah, so for liquids, delta H does change when you change the pressure, but it's very small. So we usually only consider it when it's 100 or 1,000 atmospheres. For gases, if we assume that they are ideal gases, their properties are independent of pressure. So for this class, all of our gases are going to be ideal gases for the purposes of these energy balance calculations, because real gases do have pressure dependence of the enthalpy, but we're going to neglect that because it's a fairly complicated calculation, and I don't want to steal the thunder away from your Thermo 2 class. So that's going to be a big focus in Thermo 2. Okay, so overall, what we did in the heat of reaction method is we have reactants going to products. Okay, so what we first need to do is we need to get the reactants to the standard state. We react them at the standard state. Right, this is the 25 degrees C in 1 atmosphere. And then we get the products back up to the actual process conditions. So this is exactly the same concept as the heat of vaporization challenge, right? I only know the heat of vaporization at one point that we've measured it. So I can heat the liquid or cool the liquid to that condition. I can vaporize it, then I can heat and cool the vapor back to the other state. The only difference in this analogy is that instead of it being a vaporization process, it's a reaction. So I take my reactants, I heat and cool them to the standard state, I react the system, and then I put it back to the actual process conditions. So how the heat of reaction changes as a function of temperature is the difference between heating and cooling the reactants and heating and cooling the products. If one of these takes more or less energy, then the delta H of reaction changes as the temperature changes. That's again the same exact analogy as the heat of vaporization. So the reason why the heat of vaporization gets smaller as we increase the temperature is because the liquid heats up more, the liquid has a higher heat capacity than the vapor does. Same exact analogy here. So if the heat capacities of the reactants are different than the heat capacities of the products, then the heat of reaction will change as a function of temperature, because we're going to different lengths of each of these legs. Okay, does that make sense? So I've got one more example here that I'll hammer through quickly for the heat of formation method. So conceptually, the heat of reaction method is an important thing to understand by choosing the paths that you go to. In practice, the heat of formation method is really, really quick. So we have here.
So the example we just did, that was the heat of formation.
That was heat of reaction method.
And now we're going to do heat of formation.
Yep. And I'll do this one fairly quickly because we're running low on time. So in this case, we are going to synthesize formaldehyde. So methane plus 1/2 oxygen goes to formaldehyde, CH2O plus H2. The inlet conditions are going to be 50 degrees C and 5 bar pressure. The outlet conditions are going to be 150 degrees C and also 5 bar pressure. So we're going to neglect the pressure changes because this is going to be a gas state reaction. So we're just going to focus on those temperature changes. So in the heat of formation method, we have Q is equal to the summation of the enthalpies out minus the enthalpies in. Okay. So I'm going to just build a table right away. CH4O2, CH2O, and H2. And in enthalpy in and out, enthalpy out. Okay, so let's assume that this is our material balance. 1, 0.5, 0, 0, 0, 0, 1, and 1. So this is a stoichiometric reaction. So I don't need this, I don't need this, I don't need this, I don't need this. So I just need to calculate 4 enthalpy values. Okay. This temperature is 50 degrees C. This temperature is 150 degrees C. So for any of my enthalpies, right, I'll just call this A, B, C, and D. So the enthalpy for point A, okay, this is going to be enthalpy of methane in. I first need to create the methane. Then I have to heat the methane to the process conditions. And that is going to be 25 to 50 heat capacity of methane DT. And that's the number. I calculate this, I look up the heat of formation, I crunch these numbers here, and I plop it into spot A in my table. For B, the enthalpy of the oxygen in is going to be its heat of formation. What is the heat of formation for oxygen, O2?
0.
0. Then I just need to heat from 25 to 50, heat capacity of oxygen, and I plug that number in. For C, this is going to be the enthalpy of formaldehyde out. It's going to be the heat of formation of the formaldehyde plus heating it from 25 to 150, C sub P of formaldehyde, DT. I plug that number into C. And then lastly for D, enthalpy of hydrogen out is going to be its heat of formation, which is also 0 because it's the atomic reference species, plus from 25 to 150 heat capacity of hydrogen. And plug that number in there. So the final step to determine my Q is I calculate the summation of the inlet flow rates and the inlet enthalpies. I calculate the summation of the outlet flow rates and the outlet enthalpies. And then I take the difference between them, and that gives me my Q. So I don't have specific numbers placed into here, but the procedure would just be to go to your book, look up the heat capacity of, look up the heat of formation for all the different materials, and then look up all of the different heat capacities. So with this, I wouldn't have to have made this a complete reaction, right? I could have said it only goes 20% to completion. I could say it goes 60% to completion. And that would update my material balance, but it would not affect any of my enthalpy calculations. So the further this reaction goes to completion, right, the more my Q is going to change. But if I react less and less and less, I don't have to update my energy balance at all. I don't have to update my enthalpy values at all. any change in how much the reaction progresses is lumped directly into that material balance. So in this heat of formation method, the calculation of the enthalpies is a straight up algorithm that we can trivially kind of work out. So if I were to do this problem, right, and I want to go back to the table that I built to kind of talk us through this, right? So we have heat of formation for all of my different, reactants and products. I have heat capacities here. I have normal boiling points, right? So I can just basically make one big data table. And as long as I put them in the same order here as in my calculations, I can just drag and drop my formulas. Now, let's say I didn't want to have a constant heat capacity. Well, that's pretty easy too, right? I would just look up the A, B, C, and D parameters in my heat capacity correlation, and I could just fill those numbers in directly. Now, what I do in my own calculations is I don't want to type in 2 point this times 10 to the minus this, right? What I do to troubleshoot and speed up my process is I type in the numbers here exactly as they read in the book. Then when I calculate the enthalpies in this derivative here, that's where I'll put the times 10 to the minus 5, times 10 to the minus 7, times 10 to the minus 9. So what that allows me to do is to separate my troubleshooting into 2 steps. When I look at my data tables, I color code them in a way where I say, Michael, this number is a number you directly got from the book. So when you troubleshoot, just make sure you typed in the right number with the right units, right? That makes my troubleshooting super easy. I look at my big data table and I go, yep, I typed in all those numbers correctly. I have resolved that as a source of errors. Then I go to my equations and I say, Michael, did you type in this equation correctly? And if I typed in the equation correctly, then I can just populate every single of my cells. So I only have to collect the data, read numbers directly from a book, or copy and paste them from an online table resource, paste them into my sheet, write one equation, just one equation, right? This one here. And then I just copy it down so that for O2, it grabs O2's heat of formation. It grabs O2's A, it grabs O2's B, it grabs O2's C, it grabs O2's D. Then I've populated my enthalpy calculations. I just have to plug in whatever my material balance says is the inlet and outlet conditions. And then voila, I have balanced a reacting system problem, right? So structuring your calculations in a way that allows you to take advantage of the computer is a good thing to do. So if I were to do this in Python or MATLAB, what I could do is I wouldn't name, a variable C sub P A is this for methane, C sub P B is this for methane, right? Because then I would have to like copy all these different references. So what I would do is I would have a table that says like C sub P, and it would be a matrix, right? So I would say C sub P is equal, and then it would be a big matrix, right? So it would be A for CO2 or CH4. It would be B for CH4. It would be C for CH4, and it would be D for CH4. And then it would be A for O2 and so on and so forth until we get to D for H2O, right? So if I were to do this in Python or MATLAB, an array is the same thing as a table. So then when I would write my enthalpy code, I would just say, this is for row 1, this is for row 2, this is for row 3, this is for row 4. And then my formula would refer to, 1, 1, 1, 2, 1, 3, 1, 4. And then the calculations would work out just fine, right? So if you set it up as one big table array, then you can just write a pretty trivial loop to kind of knock all those out. Okay. Do we feel a little bit better about the reference states and how to perform these calculations? Because this is sort of the last major concept that we're going to be covering, save for the transient systems. And so from here on out, it's going to be a lot of examples, kind of stress testing this, seeing what kind of calculations we can do, and then integrating it into other material balance and other calculations. Any questions?
So what if we cannot assume the change in pressure is 0? What would you want to do?
So like in the real world or in a problem?
Yeah, for example, in the real world.
That's what an equation of state is for. So in this class, we talked about how, oh, if you use the Peng-Robinson equation of state, this is what the density is, right? This is what its compressibility factor is. But in reality, equations of state are derived in order to calculate enthalpy changes and phase changes with pressure and temperature. So so in the ideal gas law, right? You have C sub P is equal to C sub V plus R. This is only for an ideal gas. And for an ideal gas, there's a complicated sort of multivariable calculus expression for how the enthalpy actually changes with pressure for any real fluid. And as it turns out, and I can send you all the links you want if you're curious. If you substitute in the ideal gas law, it does become only a function of temperature. It's not a function of pressure. But if you put in any other equation of state, like the Peng-Robinson equation of state, the Virial equation of state, the van der Waals equation of state, the enthalpy and the internal energy of a fluid is not independent of pressure. There is a pressure functionality, but it does involve some fairly complicated differential equations or calculus expressions that have to be integrated. So that's why equations of state were actually developed. It's not just for this density stuff. They use the density to tune it so that you can get out enthalpy and entropy information from it. So it's more complicated. It's totally tractable, and it can be readily automated and programmed, but it's a bit more than we want to get into in this class.
In a real world setting, is it a reasonable assumption to make that like liquids are incompressible? So like a change in pressure wouldn't correspond to a change in specific volume?
It depends on how big the pressure changes. So if I'm talking about like 10 atmospheres pressure, I don't care about the density change of water, right? So even in my research, one of the things that I look into is what is the shape of a molecule, and how does the shape of the molecule impact how it organizes, right? So how soft are those electron clouds? And that actually has a fairly significant impact on how the molecule structures and then how we can predict all of its properties. So if I want to stress test my models, I would have to pressurize my liquids to a couple of thousand atmospheres, and the density would only change a very small amount. So the expression you want to look for is the isothermal compressibility. And so that basically tells you how does the density change with respect to pressure at constant temperature. And then you can unpack that just the same way that we unpacked C sub P. And then you can actually estimate how much does the density of a liquid change when you change its pressure a certain amount. So if you wanted to play around with that, that's something that could be done as well. You could also look into your book, right? So your saturated steam tables will tell you how much does the density of liquid water change at different states, and you can kind of see how much it impacts it. But ultimately, in the real world, a lot of these thermodynamic calculations are relatively easy to program. The only limitation is having access to the data. So computers are so powerful now that if you wanted to choose a particular equation of state, you wanted to assume that it wasn't incompressible, you wanted the compressibility, those could all be programmed in and be very, very fast, provided you had the data. But for pen and paper type problems and conceptual problems like we're working on right now, it's easier just to neglect them. But in real process software that chemical engineers use to design these things, all of that would be just programmed in, provided you had the right data.
Okay. And you said it was the isothermal compressibility?
Yeah, I want to say, I don't quote me on this one 110%, but the isothermal compressibility is, I think it's alpha is the common term. I think it's 1 over V dV dP at constant T. So if you wanted to know how does the density change, you could do a separation of variables and then just assume that the isothermal compressibility is constant, and then you could just integrate it just like you did with C sub P. So
Okay.
I think it's alpha, and I think that's the definition for the isothermal compressibility. But you'll find that you got to pressurize liquids a lot before their density changes substantially. So if I wanted to change the density of a liquid by 10%, that might take a couple thousand atmospheres pressure.
Oh, okay. Awesome.
Yeah.
Thank you.
These are all properties that are measured. So that's the fun in thermodynamics, is trying to make as few of experimental measurements as possible while getting the most data out. Okay, we are well over on time. Hopefully that helped with at least finishing up the homework and then sort of solidifying what we're going to do with reacting systems. But from here on out in the homework, it's going to be a lot of reaction balances and then integrating those with material balances. So see you all on Wednesday. Remember to bring your exam regrades for Wednesday as well. All right, take care.
Really quick, Professor.
Yeah.
When are we? I was looking at the calendar since we're coming to the close of the school year. There's the project that you still haven't given us a ton of info on, and it's like due, like the first part's like due in like a week or something. Or like,
Yeah, so I'm going to adjust those due dates. So
Okay.
I'm hoping to get the project assigned today, and then we'll talk about it on Wednesday.
okay, cool.
But it's like it's not terribly onerous. It's sort of like it's kind of like it's like a homework that I want you to be organized with. Let's put it that way. So the difficulty may not be substantially more than a single homework, but I want you to be really organized about it and sort of integrate everything together. But if you follow my troubleshooting steps, it shouldn't be too catastrophic.
Okay, and then we'll have to do like the usual homework assignments on top of the project. Is that
They'll
right?
be a little bit sort of lighter because the amount of concepts that we're introducing are getting sort of thinner and thinner and thinner. And so the problems on the homework will be sort of fewer problems, maybe a little bit more involved. But if this concept of how to do the reacting balances makes sense, then each of the problems start to be sort of really similar. It's just, you just swap out what chemicals you're using and swap out what reactions are going on. So the homework will start to tamp down a little bit, and we'll give you a little bit of time for the project. But I think it's a good balance.
Thank you.
I was wondering when you were going to get this recording posted, because I was having technical difficulties for like the first half of the lecture. So I want to try to watch it before my next class.
Yeah, so let me just stop the recording right now. I'm still rolling just because I wanted to get that project information out, but I will try and get it out as soon as it like is done converting and then uploading it. So hopefully in an hour I'll have it up.
Thank you.
See ya.